Hi, I'm Tom, and today I'm going to be giving a talk on, a crash course on chip design. So let's go into that. So just to briefly go into what we'll cover. So basically we're going to give a quick overview of CPU design, specifically how CPU design has evolved. By introducing the very basics such as the fetch execute cycle and von Neumann's architecture, then go a bit into Moore's law, which is probably something you've heard of before, but explaining clearly what that is. And then there's going to be a very brief and extremely incomplete overview of CPU design, specifically with the goal of invoking curiosity so that, whilst we won't go into anything in depth, you'll be able to further research any particular topic and know what terms to search for on the web. And then finally, as we're a game studio, we'll quickly cover the implications for us as programmers because we work primarily in software, but our target hardware is the thing we write our software for. So design of that has massive implications for our day-to-day work. So what is a computer chip? Very basic. So basically, it's a piece of material. So far, they've all been made out of silicon, and it has these things called transistors, which allow for computation to be performed when provided with an electric current and inputs. This is accurate as of 2019. Maybe in the future, when you have space quantum computers, this will no longer be up to date, but I don't care about that right now. So what are we actually aiming for when we talk about a CPU? So at the very core, a CPU does something very simple. It implements something known as the fetch execute cycle. So you have a thing called a program counter, which is just an index into a piece of memory. And at that memory location and subsequent memory locations, you will have instructions that the chip is designed to be able to run. So when a chip implements the fetch execute cycle, all it does is it grabs an instruction at a given program counter address, decodes that instruction, and then runs it. And the result of that instruction will then determine what the program counter will be pointing to now. So very simple idea. And you just repeat that. And that's what a CPU does. Simple, right? So most chips implement something called the von Neumann architecture. So you've got a CPU, you've got a memory unit, and then you have some kind of input device which might affect the entire system in some way, and then obviously we care about the output. So ultimately, a CPU just processes data. And this is a high-level mental model we will use today. So it's worth pointing out that with the von Neumann architecture, that the instructions and the data those instructions operate on all reside in the same chunk of memory. And this obviously has some deep implications into what kind of software we get, especially it has implications with regards to security. But another model, for example, might be something like the Harvard architecture, where you have instruction memory and data memory walled off from each other. And this is actually used in some custom chips. And we'll come back to this because there are potentially some downsides, but also some upsides. So think about that as we continue this on. So what allows chips to get better? Because obviously, the chips we have today are very different from the chips we had 20, 30, 40 years ago. And, they've improved faster than possibly you could have imagined if you haven't been living through this transformational process of technological explosion in CPU hardware. So we'll go into that, right? 2 words, Moore's law. So what's Moore's law? So Gordon Moore, the CEO of Intel, basically predicted that the costs of components in a CPU, or the minimum component costs, the complexity for them increased at a rate of roughly a factor of 2 per year. So in practice, it means roughly, though not entirely true, chips will be twice as good every year, which is quite a fast rate. But it's worth pointing out, right, that unlike, let's say, a law of physics, this is not a real law. It's a prediction about what would happen based on things humans were doing, and there are heavy debates about it being a self-fulfilling prophecy. Because consumers were expecting their CPUs to increase at a certain rate, chip manufacturers raced to make sure they achieved those targets. The chip manufacturers didn't achieve those targets, fell by the wayside, and R&D investment had to increase exponentially in order to hit these targets. So that's something that's worth bearing in mind. So why do we get faster chips then over time? What is it about having more transistors in a chip, or any other kind of increase in our ability to produce hardware, allow the actual chips to be faster, right? We take it as a given, more transistors, faster chips, but it's more complicated than that. What is CPU speed? Can we measure it? Is it just clock cycles? Where do multi-core CPUs fit into this prediction of how fast CPUs will be? What about the instructions themselves? Are the instructions available to us on a CPU, something that affect how fast it is? And this is where chip design comes in. Similar to the way where if you build software, if you have a faster chip, you can expand the scope of what kind of software designs are achievable and what you can do with software. The same thing happens at the chip level. The more hardware you have to play with, the more the scope of your designs expands, and you've got to use that effectively. Otherwise, you're not going to get a faster chip, just a smaller one. So let's look at how an old von Neumann CPU would have been designed. So, maybe 20 years ago, we'll look at how they were designed then, and then see how, as constraints changed over time, how those designs might have changed and why. So, what are our constraints, right? So, 20 years ago, we would have had a low transistor density, so that, that's, fewer transistors per square centimeter. And, we would have had a low amount of memory, right? Memory capacity, like RAM, has scaled even faster than CPU transistor density. So those are the constraints designers were working with at the time. So what are the implications of these constraints, right? So because transistors are low density, the distance between them is high. The speed of light limits how fast information can travel from transistor to transistor. So we are limited by a fairly low clock frequency. That's constraint number one. And this leads to the CISC CPU, right? A complex instruction set computer. You have, many complicated instructions, variable length encoding. The chip design itself is fairly simple because it just implements these instructions as is. It will be single core, and you'll have an always addressable pool of memory. Because our clock cycles are so slow anyway, we can much more easily just say, I want to decode an instruction or grab some data from this piece of memory, and we'll be able to do that in something approaching a single clock cycle. And it's also worth pointing out that the reason we have many complicated instructions with variable length encoding is, memory is very limited, and you want to make sure our programs can fit into as little memory as possible. So we try to pack as much information into an instruction about that instruction, so we can actually fit our programs on disk or in memory. And then, the CPU has to do more work essentially to decompress the instructions as they get read off memory. So bear in mind, these are the trade-offs we're making there. So, CPUs have evolved over time, right? This isn't what a CPU looks like today. And it's worth bearing in mind that despite the fact that CPUs have changed so radically in the past 20 years, the way we write software generally really hasn't. And that's, potentially a concern. So let's talk a bit about how they've evolved and then go on to how that might affect the way we write software. So there's three big stories here, right? Moore's law has made CPUs much more dense in terms of, the transistors per unit area. Memory size has exploded, and also operating systems have become much more complicated for various reasons unrelated to the first two. But we're going to go into the first two for this talk, and we'll leave the third point for another time. So how do constraints change, right? So imagine you have a CPU, you have a high transistor density. It's worth pointing out that now you can have faster clock cycles potentially because the distance between transistors is smaller. So, the speed of light means that, over that same distance, we can transmit information faster, or that smaller distance. We have more heat generation potentially, right? Because, now you have many more workers essentially in a given area of your CPU. And when they process instructions, that generates heat. And, that's potentially becomes our new bottleneck. And finally, right, the way we consumers expect computers to work has changed, right? Whereas, many years ago, people, would put a cassette into their computer, and that would be the entire thing that's loaded onto the computer, and you would be able to run one program at a time. Now people expect to be able to have Facebook open, Twitter open, whilst gaming on another monitor. So that's something worth bearing in mind as well. So we'll quickly overview OS support. So basically, CPUs now have to be able to support things like virtual paging, so making sure that programs can't access each other's memory and that their access to memory are virtualized. They have to implement time slicing to divvy up time between different programs. You need this concept of privileged execution. So, the operating system is allowed to do whatever it wants. Programs running in user space have much more limited access to the hardware, which is important for security. And also, just the buses over which data is transmitted are much more genericized for various reasons. And we can cover this in depth maybe another time, but if you're interested in this stuff, now you know the words to look for. So now let's get on to the good stuff. So the things that CPUs use to take advantage of the hardware we can manufacture are instruction pipelining, RISC architectures, register file support, branch prediction, caching, and multi-core. So let's cover this. So what's instruction pipelining? So the idea behind instruction pipelining, right, is that we now have, we want to be able to achieve much faster clock cycles because we have because we want computers to run faster. And one of the ways to get a faster clock cycle is to reduce the amount of work a CPU has to do in a given clock cycle. So whereas, ages ago, the instruction for grabbing the contents of a piece of memory, loading it onto the CPU memory, performing an operation on it, and then putting it back into memory, that would have been done in a single clock cycle, right? But that's a lot of work to do in that amount of time. So now we've got more transistors to play with. We can make the overall system more complicated. But the benefit of but this overall complexity is used to make each clock cycle simpler. So the idea is instead of an instruction being a single clock cycle, we break an instruction into multiple steps. So we have a step which fetches an instruction, a step which decodes one, a step which executes it, a step which writes the results back somewhere, and each clock cycle we do one of these, and then because we've got these four different pieces of units of work in our CPU, we can do all of these in parallel, right? So whilst instruction 4 is being written back to memory, we can be executing instruction 3 at the same time, decoding instruction 2, and fetching instruction 1. And this is, a great way to improve clock speeds because we're doing more work in parallel in smaller clock cycles. But this has some trade-offs, right? Less to do each cycle, shorter cycles. But now we are limited by the longest stage of the pipeline. So if the fetch, if fetching data from some memory takes 10 milliseconds and everything else took 1 nanosecond, the entire pipeline has to run, with 10 millisecond clock cycles. That's an extreme example because we have bottlenecks. It's also worth pointing out higher frequencies means more heat. So the more and more you pipeline a CPU, the more heat you're going to generate if by having those extra clock cycles. Also, you can be really penalized by branching, because if you need to wait for an instruction to be executed before you know which branch you're going to take, then you're going to have to stall your entire pipeline until you get the results of that instruction. And the longer your pipeline is, the longer you're going to have to wait. Also, sometimes a stage might take more than one cycle. So if a given instruction requires a piece of arithmetic, that might take 5 clock cycles, and then that might potentially stall your entire pipeline. And also, you just need more silicon, and that's expensive. But that's the thing we've got, because we've got denser CPUs. And one of the things that's worth pointing out is that every single technique in CPU design we're going to discuss next are simply techniques to mitigate these negative effects of pipelining. So pipelining is what lets CPUs be faster. Everything else exists to mitigate the cost of them, and also add their own layers of complexity on top of the whole thing. Because pipelining is an important part of CPU architectures today. So, register file support. So this is, this is quite an odd concept, but the idea is that instead of having a CPU, an instruction able to work on data that's resident in memory, we actually have explicit instructions for fetching that data, storing on the CPU in what is known as a register file, operating on that data while it's on the CPU, and then explicitly writing that data back to memory. And this is good because we can have shorter instructions if you run on the same data multiple times. Because instead of having to say, do work on address XXXXXXXX and have every instruction refer to that memory address each time, we could just have one instruction which reads that data, then have short instructions which just say, now it's in register 1, we're going to do this instruction register 1 and do that loads of times, and then finally write it back. And also we don't have to fetch/store in main memory every instruction. And that's important because one of the things that hasn't changed is the fact that the CPU, which is processing all instructions, and the memory that the data and instructions are stored on, are still physically distinct pieces of hardware on your computer. And this, there's a physical distance that you can measure in centimeters or millimeters, and the speed at which the latency of data transmitting from memory to the CPU and back hasn't changed at all in the last however many years, because the speed of light hasn't changed. So the faster the CPUs get, the higher the cost it is to actually grab something from memory, to quite an extreme extent, which we'll go into in a bit. So that's a good thing about register file support, is that we don't need to fetch and store stuff in main memory every instruction anymore. But some downsides is that we need more silicon for data storage, because now the CPU has to be able to store data on it. It's hard to optimize register usage correctly. It's a really difficult problem because now the programmer or the compiler gets told what registers exist, and it has to try and optimize how they're used as effectively as possible. And this thing is a transparent to the programmer. So if a CPU next year decided to add new registers and you had more registers to play with, for example, old programs wouldn't be able to benefit from that because they wouldn't be able to use those new registers. And it's actually worth pointing out that modern CPUs use a concept called register renaming to circumvent that last problem. We won't go into it now, but search for that if you're interested. We mentioned CISC CPUs before, and CISC wasn't really a name that existed until an alternative CPU design was invented, and that design is called RISC. So where CISC stands for Complex Instruction Set CPU Architecture, RISC stands for Reduced Instruction Set Computer. So the goal is, instead of having complicated variable length instructions which can do very different things, and having specific instructions, in a CISC CPU you might have an instruction dedicated to reading a piece of memory, sending that memory to the post office, making sure the post office prints it out to a letter. That letter then gets sent to the moon, and then the spaceship crashes on the moon, and then you read the emissions from the explosions and then print that to a screen, right? Very complicated, ridiculous, things packed into tiny instructions which then need to be unpacked. RISC says we'll provide the simplest set of instructions potentially possible, and then let the programmer or compiler composite them together to achieve the desired results they want. So these are much easier to decode, even though you potentially might have to do more work in a given clock cycle. Or it might take multiple sets of instructions to achieve the same result. So this obviously has some trade-offs. So fewer cycles per instruction means we can now, we can get away with having shorter pipelines, which is good. But now we potentially need more memory to store our programs because they're going to be longer. It makes it harder to have specialized hardware for specialized instructions. And also, now we have to load data into register files before use, and we can't have, special complex instructions for working on stuff resident in memory. So, next thing, branch prediction. So as you mentioned before, branches can make pipelines behave really poorly. So one of the first things, CPUs had to try and solve is how can we reduce this cost? Because branching is something programs do all the time. So the goal here is to predict which branch the code will take before it's run, reducing the chances of a pipeline flush, or a pipeline stall. So the idea is that our program counter for running a given instruction is always going to be the same value. So every time we encounter a branch instruction, we take our program counter and use it to index a table. And then in that table, it will have information about what, we'll use it to store information about how we branched when we hit this point in the program before. And then, and this is called a pattern history table. And based on that, when we next come across, when we next know we're going to run that program counter, rather than running the instruction, or we do still run the instruction, obviously, but we load in instructions based on what this pattern history table predicts we're going to do, which is quite cool. And there's many different types of branch prediction. I'm not going to go into what they mean, but you can look these up but that's fundamentally how the data's stored, what we just described. And there's loads of these. I mean, these most of the really good prediction strategies are proprietary, and something chip manufacturers spend huge amounts of R&D on improving. So there's going to be loads of these around. But the trade-offs, are all fairly similar. We've got reduced chance of a pipeline flush or pipeline stall, because the idea is, now we're speculatively loading stuff into our pipeline. If we've got a good predictor, we're less likely to have to discard what we've processed so far and start again. But we do get lots of complexity in our CPU. And also, if our branch prediction table is limited in size, and it's very possible that two program counter indices will clash, like what you'd get in a hash table, and that can lead to bad behavior as well. So next thing, caching. As you mentioned before, with accessing memory, we are limited by the speed of light. As clock cycles have gone up, memory access latency has remained fixed. So now, RAM accesses can take, 240 cycles, which is an incredibly long amount of time, if you could be potentially running 240 instructions in that period of time. So CPUs get around this by having levels of cache. So the idea is that, for example, your register file on the CPU takes one cycle to access. Accessing, your first level of cache might take 4 cycles. Second level of cache, which is a bit bigger, might take 10 cycles. You might even have a third level of cache, which might take something like 40 cycles to access. And then finally, once you have to access memory, you then pay that massive cost. So thinking in human terms, right, if a register file access took a single day, then accessing DRAM would take 2/3 of an entire year, which is a massive explosion in the amount of time something would take. So, a quick aside, the L1 cache, quite interestingly, is often on many CPU designs separated into 2 separate caches. an instruction cache, and a data cache. And if you think back a bit, we're now almost creeping back to our Harvard design of CPU, where when it actually comes down to accessing data or instructions, when data is going through the L1 cache, we're going through a Harvard architecture. And the benefits of doing this is that we can actually optimize these cache designs for the particular data access patterns of instructions and pure data, because we know that instructions are very likely to be executed in sequence, so we can design something to accommodate that. Whereas with data, you're more likely to access it in a different way, and CPU manufacturers spend huge amounts of time seeing what the common use case patterns are here and making sure that L1 cache is really well designed to handle those. And that's something you'll come across a lot in CPU design, is that we've been talking about things like risk versus ISK. In practice and pragmatically, you have to make trade-offs. So even many RISC CPUs today will have complex instructions for very specific use cases of data processing. A good example of this, might be, operating on vectors of data. Having specific instructions for, doing an operation on 4, floats at the same time instead of doing 1. So trade-offs are always where you're at when it comes to any kind of design. So what are the trade-offs of caching? So we reduce memory access cost, which is nice, right? On average, we have to reduce, we reduce, now we can almost treat a RAM access as free, assuming it goes to the L1 cache. The other benefit of this whole system is it's invisible to the programmer, right? A hardware manufacturer can improve a cache design next year, and all the programs that run on the old CPU will be able to run on the new CPU, and the cache improvements will make programs run much faster, which is nice. The big downside to this, obviously, is that this is very invisible to the programmer. So it potentially becomes harder to optimize programs around the given behavior of a cache, because you've got no way to express to the CPU, I know I'm going to use this data, so please cache it for me. This is designed to be transparent, and whilst that's a blessing, it can also be a curse. And the big downside, right, is that this is incredibly visible to the programmer. If due to bad cache behavior, your program runs 240 times slower than it would have otherwise, that is going to affect your program. The problems you are trying to solve depend on the latency constraints you have. The consumer is going to see that. And because it's potentially difficult to reason about this because of the way this stuff's exposed, you have to be careful because it's going to impact you a lot. So in practice, whilst we would like to think we would write programs in a cache agnostic way, in practice, caches have very known performance characteristics or well-known performance characteristics. And if you want your programs to run fast, you have to take those into account. And that's incredibly important. And that's, if there's any takeaway from this talk, it's always think about the cache when writing programs. Because this is where you can get your biggest slowdown and performance improvements as well, if you use them well. So finally, multi-core support. So the idea is we have more CPU, more space to design a CPU on. Instead of having deeper pipelines, then all the trade-offs and design complexities we described earlier to mitigate the effects of those, why don't we just instead say, let's not worry about having super high clock cycles. Let's have slightly smaller pipelines, reduce loads of complexity about making us, allowing us to use them effectively, and now just have multiple CPUs on the same chip, right? Because we just have to make the pipeline a tiny bit shorter. We might be able to make the entire CPU, half as complex. Now I can fit 2 of them on the same chip. They can both run at half the clock rate, which is great because, we're going to produce much less heat. And then on top of that, we still potentially have the same theoretical throughput as we did before, because even though we're running at half the clock cycle, we're doing 2 instructions at the same time. So, but obviously this has a lot of trade-offs, and anyone who's worked in software and had to write multi-core code will probably be very well aware of these. So you get your lower clock speeds and heats, you get simpler pipelines, but now your programs are massively more complex because you now have, an extra element source of non-deterministic behavior. You can have race conditions as you have to coordinate data access. The cache has to become more complex because now you will have different, cores on your CPU. They might need different caches. You've got to coordinate between those caches. So now your design complexity of the CPU itself increases exponentially. You may need to do more I/O operations. Your theoretical limits might be limited by Armdahl's law, right? If that, sometimes you can only do things in sequence. So, if, if 10% of your program has to be done sequentially, you might have 1 million CPUs or million cores on your PC. That 10% is never going to get any faster. And there's too many negative points to count here. But in practice, the first 2 points are so powerful that, multi-core chips have, ended up being worth it. And also there have been many improvements made in the way we write software, or some improvements made which are making these problems easier to solve as well from a software perspective. So, bringing it all together, we briefly covered the physics layer. CPUs are made out of silicon. We discovered at a very high level what a CPU actually is. We covered very briefly what Moore's law was and the implications of that. And then we gave a brief and incomplete history of CPU design, so you might have a better idea of how CPUs have evolved over time in order to fit this Moore's law curve. So, what are the implications for you? Basically, the design of hardware has a massive effect on the software that runs on it. We ultimately write software to run on hardware. That is our target platform. And, increased design in hardware complexity has, resulted in a massive increase in the importance, prevalence, and necessity of software abstractions, because we don't want to have to think about this. So we write software, compilers, to take, stuff which is written in an abstract, fairly abstract way, and we'll then process it and try to optimize it in a way that runs effectively on the CPU. But paradoxically, these complex CPU designs mean that subtle changes in the way we write programs can have massive effects on functionality and performance in a way many tools can't even reason about, right? A C++ compiler can't change a data memory layout to more effectively use a cache, for example. So whilst, and this is worth bearing in mind and extremely important, that now we have to think about the complexity of hardware potentially more than we ever did. And whilst, powerful hardware now means, the performance impact of an application isolation is negligible, right? When you program, when you write a program and you profile it, it might be very hard to actually get any meaningful data values out of it because it runs so quickly. But because we're asking our computer to multitask more and more every day, the sum total, if your program, if you're testing your program in isolation on a computer, especially if you're developing a user-facing application, then a 10% performance hit might not be noticeable if that's the only thing on your dev computer as you're working day to day. But then a consumer who has 100 programs installed, which are all 10% slower than they would be otherwise if these performance degradations were more transparent to the software developers developing the programs, then the sum total can still be really bad, and we actually should still be comparing about performance in the context of multitasking, which is becoming an ever more complex problem. So, final points. I just hope you have found this interesting. The second point is hardware design is important, even if you work in software, because that is a target platform. It's worth pointing out multi-core is here to stay. We need to learn how to use it. And finally, memory access patterns are a big deal. Please be cache friendly.